Ladies and gentlemen, we're back here at Innovation Stage at EMO Trade Show 2025 in Hanover, and I'm especially looking forward to the next presentation. And this is why. This morning we learned about energy efficiency in manufacturing and tracking energy efficiency, and that is not a standard yet with most of the machine tool manufacturers. And the next presentation by Marc-André Dittrich, Manager Central Development Coordination and Research Manager at DMG Mori, will tell us about a solution that is used at DMG Mori, and he will present that solution to us, how energy efficiency can be tracked. Marc-André, the stage is yours. Thank you very much. I'm delighted to be here at this beautiful stage and to tell you about energy efficiency of metal cutting machine tools. Why is that necessary? Why do we as manufacturing companies, as machine tool manufacturers, need to look at energy efficiency in the first place? Now let's take a look at the global annual electrical energy demand. You can see that here on the left, and the global electricity demand of 2023 amounted to almost 30,000 terawatt hours. 38% of that were accounted for by industry, and 3% were accounted for by machine tools. Metal cutting machine tools account for 2%, and it depends on the source here, the energy sources here. And that is roughly 580 terawatt hours. I find it very hard to imagine how much a terawatt hour is. So in order to give you a comparison, the electrical energy demand for Germany for 2023 was at 517 terawatt hours, and Japan, with a bigger population, was at 939 terawatt hours. So metal cutting machine tools account for the electrical energy demand of entire nations. So it is really worth it to think about this. And the next question here is, where's the electricity demand for a metal cutting machine even coming from? Now, I could make things simple for myself. I take the documentation of the machine tool and I look at the different electricity source connections. But that is only half of the truth, because some components, such as spindles, they are high-performance tools, and they are designed for high-performance tooling, and they give us a wrong picture, so to say. And you can see here on this slide that typically the demand for spindles and feed drives is somewhere between 25 and 30%. A significant share of energy goes into the cooling of the machine. 14% is used for machine cooling, 2% for the control cabinet cooling, and very high shares used for process cooling. And this depends on the way I'm manufacturing. And there's also other parts. Coolant mist extraction is at 9%, and compressed air demand. Let's not forget about that. Now, what can we do in order to reduce our energy demand? There's two options here. First, it's pretty clear. The first approach is that I use energy-efficient components that reduces the energy intake of the machine directly, the energy demand, and this is basic physics. Energy is performance times time. This depends on the time. If I can produce a part quicker, I have automatically a second way of reducing energy. Now, how can we manage to combine the two? That is when we get efficient manufacturing generally, and I would like to take a look at the two in more detail to show you how the energy demand of a machine can be reduced, and then also show you a few options for the automation to reduce downtimes and low production times, so that one workpiece can be produced in an energy efficient way. Now, let's start with the energy efficient components. What can I do here? A first step would be to use drive systems that come with a high energy efficiency class, for example, for spindles. The drive systems cannot be over-dimensional, so they need to be dimensioned according to the machining task, and they need to be able to do recuperation. As we just saw, chillers are also a major energy consumers in these machines. Unfortunately, today, often these chillers are highly inefficient. What would be a lot more efficient here would be technologies such as cold water mixtures or frequency-regulated aggregates. And the most efficient way to connect them directly to your whole infrastructure, workshop infrastructure, and use heat exchangers for that. I also mentioned process cooling. For process cooling, we see that the use of frequency-controlled pumps can play a major role, and adaptive coolant supply, and I will go into more detail on that later on, as well as an efficient mist extraction. Compressed air is a hidden energy consumer. Often we don't see compressed air. We can hear it if there are leakages, but as we saw earlier, 20% of the energy demand is accounted for by compressed air, so a reduced air demand, for example, through scales without air purging, or monitoring my air consumption and detect leakages early in order to counteract them. Now, further measures could be to come up with more transparency by means of energy monitoring, an auto shutdown function to establish, increase the efficiency of hydraulics with accumulators and boosters, and to have frequency-controlled hydraulic pumps. Now, let's take a look at specific examples that we have at DMG Mori. Let's look at monitoring of the electrical energy demand. Our machines are mainly standard machines with electrical energy monitoring. That means that we have the opportunity to measure electrical energy demand and to have specific analysis of the energy demand, to look at specific parts of the process and see the energy demand. You can see that here on the right, so that you can see exactly where you can adjust the energy demand and where you cannot. We also do calculation of CO2 emissions and a calculation of the energy costs, and this can be adjusted by a compressed air measurement system. This is the advanced auto shutdown. It enables you to shut down your machine and aggregates in standby. So you can tell the machine beforehand which aggregates to shut down and when they need to be switched on again, because you don't want to wait until you can manufacture. You want running machines at the beginning of your shift. Now, I mentioned compressed air twice already, and one innovation that we are presenting here, the EMO, that's pneumatics monitoring. Compressed air can account for 20 to 30% of the total energy demand, and if we monitor the air demand, we get information on whether everything is okay with the machine in general. In addition to that, you can detect air leakages and counteract them on the basis of a fingerprint that constantly compares whether there are leakages or not, and then on the basis of that, warnings are sent out. Now, let's take a look at the energy demand for cooling lubricant supply. If we work a piece such as the one on the left with 80 bar during cooling, 23% of the total energy demand will only be accounted for the cooling lubricant supply. And the rest, the 77%, are accounted for by other consumers. So the question here is that necessary? Do we need to use that much energy only in order to cool the entire production? Well, let's take a look at this in more detail. What is happening when we cool our process? The pump that we use tries, we're talking about tiny drillings. So air is pressed into this. You can see that here on the diagram. 80 bar is used, the connection between the throughput and the performance rate of the pump is not linear. At the same time, over the past decades, we have seen improvements in the cutting processes. So often the cooling is not needed that we are using for the 80 bar processes. We need a lot less coolant. So the throughput can be reduced by 45% and the performance input of the pump can be reduced by 80%. So there's that non-linear link between the two, and we can reduce the coolant flow, and that's what we do with adapted coolant flow. We do not adjust the pressure, we adjust the flow of coolant volume, and that's independent of the hydraulic resistance. At peak performance for a borehole, for example, you'd have a stable amount of coolant flow. So the flow rate, the control of the flow rate enables the stable cooling lubricant supply. And I would like to show you this with a video. Before machining, you pick ACF, adaptive coolant flow. You can see that here. The employee is picking the basic option. So anytime an unknown new machine tool is clamped onto the machine is going through volume and pressure steps. It is thereby detected how much energy it is using, and then this is inserted automatically into the machine's catalog, and every time this tool comes up, the machine knows the amount of coolant that is needed. And on the left-hand side, you can see the situation without ACF, and you can see the performance, the watts at the top, and here you can see that we can save between 80 and 90% with the pump. There are secondary effects, less oil use, we need less cooling fluid, and in some cases with very slim boreholes we can see a quality increase, and that is because the tool is not moving to the left and right if there's a lot of pressure applied. Now let's look at some more numbers, facts and figures, and the comparison between an 80 bar power and the power with ACF. You can see the various tools at the top, a milling tool, for example. You can see the sizes, and at the bottom you can see the pump power at 80 bar with ACF, and then the relative and absolute differences. For all of the tools, you can see now here that we can save up to 80% of energy. Now let's apply that to the total energy demand of the machine. You realize that there's a 20% energy saving potential when manufacturing this workpiece. So that's a major lever. A question that could arise here is how does machine wear play a role here, and we tested that with different machine tool manufacturers. What you can see here is an example for boreholes of 42 chromo 4 from the first boreholes of 465 holes to 1,433. We have various types of machine wear. You can see the different colors for 4 different coolant strategies with 40 bar. So reference that's and 80 bar in red. We have 18 bar and 7.35 liters per minute. That is what we do through the ACF. There's no significant difference in these graphs. So ACF does account for energy saving, but it doesn't change the tool wear. Now, we looked at some technologies in a lot of detail. Let's now go to a broader level. Let's look at the DMU 75 monoblock tool machine. And here you can see the various states of the machine. There's the standby machine, the machine under warm-up, the machine under NC ready, the machine during machining or during emergency stop. And typically, energy demand is between 3.5 and 17.3 kilowatt hours. Now, if we implement energy-reducing measures, automatic shutdown function, and adaptive ACF, and so on, you can see here that for any machine state, there are major energy-saving potentials here. Now, let's look at what this could mean for the general use of a machine over 1 year. The saving potential is up to €3,578 per year in energy costs, and 50,000 kilowatt hours per year is the usual value, and with the energy saving measures we can reduce that by 17,890 kilowatt hours per year. That is just one example on the base of a few measured facts and figures. This always depends on your type of production, but this is to show you the potential of these measures and the costs and CO2 emissions that you can also save through this. Now, what can I do through energy-efficient components? That was the first part that we wanted to look at, and the second part is the energy savings through process integration. And I brought you an example here from our own manufacturing process. You here have the manufacturing of a machine part. We manufacture that in Japan. There are 7 processes in 7 machines. You can see that at the top here. And a process time of 470 minutes is the result here. Energy consumption is at 134.1 kilowatt hours per component. That translates into 56.9 kilograms in CO2 emissions. We looked at the steps of the process, we optimized the processes, and we were able to reduce process time to 199 minutes. That's a saving of almost 58%. Energy consumption was reduced by 54.4 reduction, and that accounts for 39 kilogram CO2 emission savings per workpiece. And we were able to reduce these 7 processes and 7 machines to 2 processes in 1 machine. And this is a major contribution to energy savings. Now, that is the end of my presentation. I would like to wrap this up and give you a summary. We saw that the energy demand in machining is dominated by auxiliary machine tool units. I think that's a major takeaway message here. An efficient machining requires a combination of high productivity and energy-efficient machine components and low downtimes and non-productive times. Whenever the machine is there and it is not in use, it's still consuming energy, which is why there is a major influence on overall energy consumption. We saw that with state-of-the-art technologies, energy savings of over 30% can be achieved, and with that, energy solutions help a lot in order to render the energy demand transparent and to detect leakages, and that is a very, very important approach. That's where you can start your energy optimization processes, and what is it worth at the end. With the ACF, I showed you a technology that enables you to lower the energy, the performance within the process significantly, and that is a plea to you. Look at the energy you use for your workpieces, do you use 80 bar in pressure? Is that really necessary? You can reduce that maybe to 40 bar and you can save a lot of energy there. And last but not least, I presented the second part to you, process integration and process automation in order to reduce your energy consumption. We have a white paper. It is available online for your download. It is named Energy Efficiency of Metal Cutting Machine Tools. You can download it in English and in German. And many of the things I just explained to you in this white paper. And on that note, I would like to thank you for your attention, and I'm ready to answer any of your questions. Give them a big hand. Thank you very much. I'm personally always very happy if I see a new product. Yes, that's always nice to see. But to really look at every single aspect to reduce energy consumption, and that was the focus of this presentation. I would be interested in the following. If you go and talk to your clients, and do you think that they know about this or not? Well, this depends. We do have clients who are really aware of this topic and who are really interested, and they have already made a lot of progress when it comes to this. But often with these hidden consumers, compressed air, for example, those are the topics that people don't often know about. And in my presentation, we were able to see that they do come with a lot of potential for energy saving. And I would like to encourage everybody to inform yourselves. Those are really low-hanging fruits that you can start with. The problem is with low-hanging fruits that they often hang too low so that you just hit them with your head. Well, you've been doing this for a while. You do energy transparency. Everybody knows about energy prices. Whenever I have energy transparency, it is a very simple way to calculate return on investment when I have my energy data. When is this really worth it, and is that a reason to approach your clients? Well, it's difficult. The increased energy price, especially for Germany, it is rather high as opposed to other countries. But the payoff of this technology takes quite a long while, so we would like to standardize this process. And this is a process that takes time to really, for this to be really present in the entire industry. And many of the solutions that I just presented you, they are often not only an option, they need to become a standard part of the machine. We went on a trip through the entire machine with you. The coolant and the lubricants, they come with a lot of potential here. Do you talk to manufacturers of these lubricants and coolants, or are the solutions all on the machine side of things? Well, it's the entire ecosystem. The machine tool manufacturers are just as important as the coolant and lubricant manufacturers, and additives, for example. How are the additives working on the machine tool when the machine tool is cutting something between the machine tool and the workpiece? And that all of these factors influence the type of coolant, the type of lubricant I need to use, and how they work together. And optimizing these coolants and lubricants always depends on the tool and on the process. So come and see us in Hall 2. That is really the best way to do it. Tell us your specific case, and then you can look at the technology cycle, and then you can understand how that works. And that was the perfect invitation. Thank you very much. Give them a big round of applause. Great presentation. Thank you very much. Go and see the DMG Mori booth. I guess you will be there. Thank you very much.